Hello everyone, welcome to Robotics 2. Today we're going to do an example with a manipulator with 2 degrees of freedom, 2 joints. And what we're going to do is find the velocity of both point J and point I. And I may do a couple of videos on this with a couple of different methods to show you. But we're going to start out with just a basic differentiation of positional vectors, basically, or positional matrices. So starting out with that, the velocity of point J. We need to start with this because J is the first point in the system. We can basically ignore the rest of the system when we're just looking at J. So we know it's 4 from here, some value G from here, and 1 from here. You may be wondering, well, what the heck is G? I just used a variable here because it really doesn't matter what G is, and you'll see why in a minute. Because this is equal to I R1 dot. So the rotational rate of of 1 with respect to I, so basically this point here, or this axis, plus I t dot 1, 1, 1, r, j. So the translational vector from 1 to j with respect to 1, and then the transformation from 1 to I. I know that's a little bit backwards, but this is basically so these ones can cancel and you can get IRJ. Okay. So if you look at this, if you take the derivative of this vector, which is from here to there, it's going to be 0 because the derivative of any set of constants is 0. So this is going to be 0. This, on the other hand, well, we have a rotation about z, which is going to be cosine, negative sine, 0, sine, cosine, 0, 0, 0, 1. I'm not going to write that out because hopefully you're aware of this, but this is going to be rotation about z. And you use that matrix, that's transformational matrix. And this is going to be 4, 4, 0, 0, right here. So the rotational matrix of about z times 4, 0, 0. If you multiply that all out, you're going to end up with 0 plus negative 4 theta dot 1 sine of theta 1 cosine of theta 1 for theta dot 1, 0. Alright, I skipped about 5 steps in that leap from there. I took the derivative of this matrix and multiplied it by that matrix and showed you what it was. Hopefully you're able to do that math, but this problem is going to be pretty long as it is, so I don't really want to show that right now. So, this is the rotational rate of J, or the velocity of J. So congratulations, we just got IIRJ dot. That's the first part of our problem. We have J. Great. Now we need to find I. And I is through a couple of different rotations. We also have a theta right here, theta 2, and a theta 1 right here. I forgot to put those in the problem, but that's where the theta is coming from, this theta 1. Okay, so if we are trying to find II dot Ri is equal to, it is equal to II R2 dot plus I T2 to Ri. Now we don't have this value yet because this value we actually have to go through a joint in order to get it. So we need to expand this out in order to solve for it. So this entire problem is going to be II R1 dot, which is the rotational rate around here basically of I, plus, or of 1 at this point, I apologize, and then the rotational rate, which I'll show right here, which is I T1 dot 1, 1, R2, plus I T2 dot 2, 2, Ri. So, if you look at this, you'll see something kind of familiar, and it's this piece right here, as well as this piece. We know this piece goes to 0, because again, it's the derivative of the straight vector right here, which has no motion associated with it, because they're both fixed points. And then this we just solved for, but with respect to J. But the only difference between J and 2, this axis 2 right here, we'll call this 1 and this one 2, is that this is 4 and this is 5. So basically, to solve for this, all you have to do is change these 4s to 5, because that's all that's going to change. It's still rotating about z, and it still has some length, fixed length. In this case, we're just going to change to 5 now, going through into point 2. So in solving this out, if you do this piece and this piece here, where this piece is going to be rotation about z, derivative of it again, of theta 1 plus theta 2. Okay. Actually, I'll show you all this stuff. So we have this, we have this, we have this. We need to solve for this piece. So, IT2. It is equal to IT1, 1T2. So the transformation from here to here, and then from here to here, and then so on. Okay, this is equal to a rotation about z of theta 1, and then a rotation about z of theta 2. So to get from I to 1, we have to rotate about theta 1, and then to get from 1 to 2, we have to rotate around theta 2. Rotation about z, this is equal to a rotation of z of theta 1 plus theta 2. Get it up there where you can see it. Which is then equal to cosine of theta 1 plus theta 2. I'll write out the whole rotational matrix just like I didn't do up here. Minus sine of theta 1 plus theta 2. 0. Sine of theta 1 plus theta 2. Cosine of theta 1 plus theta 2. 0, 1, 0, 0. Just like that. Okay, and now we take the derivative of this because we want to get IT2 dot, which is what we're going for right here. So IT2 dot, the derivative of this entire thing, is basically going to be this dotted times the derivative of this, which is going to be negative theta 1 dot plus theta 2 dot. Actually, I'm not going to write this all out, because hopefully you guys can do this on your own. Plus theta 2 minus theta 1 dot plus theta 2 dot cosine of theta 1 plus theta 2, 0, 0, 0, 0, 0, and stuff in here. Hopefully you guys can do the derivatives of these two right here. It's just like this. Alrighty, so now we have theta theta 2 dot. So we can check that mark off. If we multiply that now by 2 Ri, this is going to be equal to 3, 0, 0. Because, looking at this again, on this vector, in relation to this vector, you move along the x3 and you move in no other directions. So 2 Ri, from 2 to I, with respect to frame 2, you move along the x-axis 3. So that's where that vector comes from. We're going to multiply it by this matrix, which hopefully you just made. And what you'll end up with is IT2 dot 2 Ri is equal to negative 3 of theta 1 dot plus theta 2 dot sine of theta 1 plus theta 2, 3 of theta 1 dot plus theta 2 dot cosine of theta 1 dot plus theta 2 dot all over 0. That's what will happen when you multiply this matrix by this vector. Okay, so now to get IIRI, the entire thing, we take this, which is going to be 0, this, which is going to be this vector with 5s instead of 4s, and then this, which we just figured out. So I'll write that all out. IIRI is going to be equal to 0 plus negative 5 theta 1 sine of theta 1, 5 theta 1 dot, sorry this is dot, cosine of theta 1, 0, plus negative 3 of theta 1 dot plus theta 2 dot sine of theta 1 plus theta 2. Oh, let me get this up here so you guys can see it. 3 of theta 1 dot plus theta 2 dot cosine of theta 1 dot plus theta 2, not dots. This should not be dots. I got carried away with my dots. That should just be theta 1 and theta 2. All over 0. Adding those all up shouldn't be that difficult because it's pretty basic addition. So and I lost my lead right now. There we go. So Ri is equal to negative 5 theta dot 1 sine of theta 1 minus 3 theta 1 dot plus theta 2 dot sine of theta 1 plus theta 2, 5 theta 1 dot cosine of theta 1 plus 3 of theta 1 dot plus theta 2 dot cosine of theta 1 plus theta 2, 0. And that is the velocity of point I in reference to frame large I. And there's another way to do this, but I may do that in another video in case you want to see a different method of it, where you basically use angular rotation vectors, vectors of angular velocity basically, and multiply it by the transformation matrix instead of taking the derivative of these matrices like this, which is kind of handy if you don't want to do all this differentiation by hand or you have a more complicated function. All right.